Welcome back. We have solved Santa's biggest problems. With unique pointers, he could hold the list safely. With shared pointers, he could share it with other elves without copying. But what if there are some trainee elves who are just there to observe? Welcome to the season finale of Learn C++ with me. Today, we tackle weak pointers. Imagine Santa has some elves on standby. They don't need to own the list, they just need to know if it still exists. We want to give them a ticket, which can be redeemed for a shared pointer, but it should not block the freeing of memory once all elves and Santa are done working on the list. This ticket is called weak pointer. And today we will build weak pointer from scratch. Okay, let's pick up where we left off. We have the shared pointer, but to support our weak pointer, we need to change our architecture. Remember how redundant it felt to manage the data and counter separately? Let's fix that. We're going to extract the list pointer, the size, and the count into a separate struct called control block. Think of this control block as the shared whiteboard. Santa and elves don't hold the list directly. They hold a pointer to this whiteboard. Like so. Now we update the nice list class to hold just one data member, a pointer to the control block. In our constructor, now, instead of allocating all the data members separately, we will just allocate one new control block on the heap. This control block will act as our indirection pointer. If this pointer is null, the whole list is considered to be invalid. Let's update the code. So the control block will have some address OX40, let's say, and at this address OX40 we'll have the data members with default values. Count is 1. Our list is a null pointer, meaning that it's not been allocated yet, and the size is 0. Now for the rule of 5, starting with the destructor. Since the control block handles all the raw pointers and the data members, we delegate the cleanup to it. We delete the list and we set the size to 0. But watch closely. When the reference count hits 0, we clean up the data list, but we do not delete the control block itself yet. This is crucial. The whiteboard must stay up as long as there are observers watching it. Next, the copy operators. See how much simpler and neater our code becomes? Because of a refactor, this is now much cleaner. We simply copy the pointer to the control block and increment the count. The benefits of encapsulation are really showing here. Same for the move operators. We simply steal the control block pointer and nullify the control block pointer of the right hand side. Simple, fast, efficient. Finally, we update the pushback function. We don't even need to declare new variables because our code is much more neater. We allocate a new list. We copy the list to that size into the new allocated memory. Delete the old list. Point the old pointer to the new list and write at the updated size the new value. It's a simple replacement, just dereferencing the control block and copying the data. Let's get the other errors as well. To wrap our heads around the control block, let's just visualize a minimal set of functions. We have the control block, the constructor, the pushback, and the destructor. This is by no means a memory proof function, but it helps us to understand how the control block acts as our shared whiteboard. This is the simple driver code that we'll be running, just 3 pushbacks. First, we construct a nice list which just allocates a new block with the default values. This is our shared whiteboard on the heap. Next, we push back 5 into this list. So a new list is allocated. The old list is deleted. It's the pointer for the list points to this new list, and we write the past value into the new allocated memory. Do this again. Copy, delete old, point to the newly allocated, write the new value. And again. And then we come to the cleanup. So if the control block exists, we decrement the count. If the count is 0, we clean up the data, which is cleaning the list and setting the size to 0. And then we come back. Now, of course, the control block is leaking memory at this point in our code, and now we will see how we tackle that. Now let's compile and run the code to this point with the following driver code. This is the same driver code we had for shared list. Okay, so far so same. We create, increment the reference count, we copy, we move, and everything seems to be working just as it was in the shared pointer example. Good. So far so good. Now finally let's add the logic for our observers, the trainee elves. First thing first, to our control block we add a week count, which is the number of trainee elves observing it without owning the list. And here is the update to our destructor rule. We only free the control block if nobody is observing it. Preventing any data spillage and also keeping the control block alive if even if all the main elves and Santa are done working with it, but there are some trainee elves who are just observing it. Of course, if the main count is 0 as well. So yeah. Let's just compile and run our code to see that everything works. Oops. So far, so good. And finally, we have deleted the control block as well. So there are no memory leaks either. So how do we create these observers? We need a new class, the weak list. Remember the ticket analogy? This class is that ticket. It holds the pointer to control block, but it does not prevent the data from being deleted. Now let's write the constructor. A weak list cannot exist on its own. It must be created from an existing nice list. So what do? We grab the control block if the list exists. But we have a problem. The control block is private inside the nice list. We don't want to make it public for everyone, so we introduce a new keyword, friend. This lets the nice list know that weak list can access those private members. So we copy the control block, we increment the weak count, and write a debug statement. If the control block does not exist, that means the list has been moved or is invalid. Then we just return a null pointer. Now, for the most important function, the redeem function. This is how a trainee elf attempts to become an active worker. They try to trade their ticket for a real nice list. That's our return type, nice list. We have to check two things. Does the control block exist? And is the strong count greater than 0? That is the list still being worked on? If the data has already been deleted by Santa, the ticket is worthless. So we will return a null pointer. But if the data is still alive, we need to return a new list, and this one has to be constructed from the control block. But currently, we don't have a way to construct a nice list from an existing control block. So let's quickly write a private constructor to nice list to handle this. It takes the block and increments the strong count. We'll add a debug statement as well. And also for the weak pointers. Ticket valid. Nice list redeemed. Ticket invalid or ticket expired. We have a new class and you know the drill. We need to implement the rule of 5 to stay memory safe. By now we have done this a few times. So the first thing we start with is the destructor. We follow the same pattern as before because we know we'll need to have the cleanup in the copy operators. When the weak list dies, we decrement the weak count. we always need to be a little more careful because the list may have moved. So we always need to check for the existence of the control block so as not to get a segmentation fault. Perfect. Decrement week count to week count. But then, do we hit delete? We strictly do not touch the data list. That's Santa's job and the other senior Ls who are working on it. We only delete the control block itself and if we are the very last one out the door, because very graciously that's been left for us. That means checking if the weak count is 0 and the strong count is 0. If both are empty, we turn off the lights and we free the memory. If weak count is 0, so there are no observers, and all the senior Ls and Santa are also done, then we delete the control block and add a debug statement, no observers, deleting the control block. Next, the copy operators. Unlike the nice list, creating a copy of weak list is very lightweight. We aren't managing any memory. We aren't creating a new control block. We're simply handing out another ticket to the same show. So we copy the pointer So we copy the pointer and then we increment the week count. For the assignment operator, remember the drill. Check for self-assignment, clean up the old resource, decrement its count, and then attach to the new one. So check for self-assignment. Return this. Clean up the old operator which handles the decrement. And then just copy the resource and increment the week count. And finally, the move operators. These are even more straightforward. Since we're just transferring the ticket from one elf to another, the total number of observers doesn't actually change. We simply steal the control block reference and nullify the right hand side. Remember double ampersand? we just nullify the right hand side. Check for self assignment. Clean up. Steal. Nullify. There's a small correction in the code. In the redeem function, I misunderstood what we have to do. We actually do not decrement the week count when we're redeeming it. The ticket remains valid for as many times as we may want to redeem it. That's just an implementation detail. This is how week pointers are implemented. So we don't decrement the week count in redeem. Another small nice to have is that whenever we're deleting the control block, we can assign it to null pointer. It doesn't change anything. It just makes for a more neater execution. Also, the print statement should be inside the if block. And one more thing, we are adding a null pointer guard on the construction of nice list, because if the ticket has already expired like so, and we call this, then we don't want to increment the count, otherwise that will lead to a seg fault. So let's look at the driver code and compile and run this and see the output. It's a fairly simple code. We create a current list and we do it on the heap because we want to delete it later. We push some values into it. We create a week list from this. We redeem it. We delete it, and then we try to redeem it again. And we expect this to show to tell us that the ticket has expired. So let's compile and run this code. Okay, as we can see, we first push two references into it, create a week list, increment the reference count, redeem it, and we are able to redeem one ticket. When we redeem it, the ref count increases to 2, and immediately, because after redemption we aren't storing anything, the destructor is called and the ref count again decrements to 1. Then we call delete cur and the reference count deletes to 0. Crucially, only the data is cleaned up. There is still an observer and we don't get this statement out. Observer count 0, deleting control block. So the control block still lives. Again, when we try to redeem the ticket has expired. After this, the week reference also goes out of memory and it decrements the week count to 0. Now, finally, when there are no observers and no active workers, the control block is also deleted. Next, we will visualize this in Python tutor. So I have removed all the printf statements, but the main logic remains the same. First, a nice list is created. Then we push 5 and 7 into it by the same way that we have always done. Next, a weak list elf is created, which increments the weak count and just returns a pointer to the control block. Now it's redeemed. When it is redeemed, it first creates a nice list from the control block and the count increments to 2. As soon as the redemption is over, because there is no assignment, the destructor of this newly created nice list is called. So PyTutor is not able to visualize this pointer, but basically because it's a temporary object, it refers to this control block, as we will see here. So when it says count minus minus, the count decreases. See? Now the count is not 0, so we just return. Now we delete the list. The count decrements to 0. If the count is 0, we delete the data members. But because we still have an observer elf whose weak count is 1, we don't delete the control block. Next, we try to redeem again, but no luck because the ticket has already expired. Now, we call the clean constructor for the nice list which was created with the null pointer. Now the weak pointer, the weak reference itself goes out of memory and its destructor is called. Its destructor decrements the weak count, deletes the control block, and voila, here we have it. A weak pointer without any memory leaks. And there we have it, the final piece of the puzzle. 3 weeks ago, we were dealing with raw pointers and manual memory management. Today you have a fully robust memory management system with unique pointer, shared pointer, and now weak pointer, all built from scratch by you. We went from basic RAII to implementing move semantics, reference counting, and finally the control block architecture. This isn't just tutorial code. This is the same logic that powers unique pointer, shared pointer, and weak pointer in the standard library software all over the world. We started this journey with a simple problem. Santa needed a safe way to hold his list. We built unique pointers to give him exclusive ownership. We built shared pointers so he could work alongside with his head elves. And today, we tore our code apart and rebuilt it with a professional control block to create weak pointers, allowing the trainee elves to observe the list without accidentally keeping it alive forever. If you have been with me since the first episode, thank you. We didn't just learn how to use smart pointers, we learned how they work. We battled memory leak, mastered the rule of 5, and conquered refactoring. You now possess the knowledge to build the standard library tools from scratch. So pat yourself on the back. This brings our C++ Smart Pointer season to a close. I hope you have enjoyed learning C++ with me as much as I enjoyed making it. Thank you so much for watching. Keep coding, and from bottom of my heart, happy new year 2026. Let's make this next year the best one yet, and I will see you again in the new year in my next series. Thank you. Like, subscribe, share. Thanks.